My name is David Layden. I'm currently doing a PhD in the quantum engineering group at MIT. And I'd like to tell you today about a new generation of technologies that go by the term of quantum technology. Now, this has a slightly different flavor than a lot of what we've seen so far today. This is really something that's grounded in physics instead of biology. So our story today has two parts. In part one, I'd like to take you on a whirlwind tour of quantum physics and tell you about two important phenomena that are called quantum superposition and entanglement. In the second part, I'd like to show you how we actually use these fundamental phenomena to make useful new devices. And so in particular, I'm going to talk about three applications called quantum communication, quantum sensing, and finally quantum computing. And to wrap it all up, we're going to talk about what this might mean for us down the road. So quantum physics came on the scene early in the 20th century. And the reason for it was that scientists got to a place in their experiments where they were able to probe down to the behavior of individual atoms, so down to the very building blocks of us and everything around us. And what they started to find was that the physics that they knew at the time was doing a pretty bad job of explaining what goes on at the atomic level. So more or less your high school physics really doesn't get right what happens inside of an atom. And so they had to develop a whole new theory, a whole new set of rules, if you will, that were called quantum physics or quantum mechanics that describe how things work at the very smallest scales. Now, the thing to keep in mind as we dive into this quantum realm are the sizes that we're going to be dealing with. So most of what we were familiar with in our day-to-day lives is maybe somewhere in this area here. Somewhere maybe between the size of a person and maybe a dust mite at the lower end. Now, a lot of our current technology, for instance, the processor on your phone, maybe that has components that go all the way down here. But when we're talking about quantum physics and quantum technology, we're really going to be mostly concerned about this area down here. And so it shouldn't be so surprising to us when we encounter some things down here that seem odd or counterintuitive, because our intuition is really not formed in these length scales over here. It's formed way further down on this chart. And so to explain how things work down here, I'd like to use coins as a metaphor. So if I have a normal coin, like the quarter I'm holding in my hand here, I could flip this and maybe it'll come up heads, or I could do it again and maybe this time it comes up tails. The key point is that it's always one or the other, but of course not both. If instead I somehow had a quantum coin, something maybe about the size of an atom, if I flipped this quantum coin, it can actually sit for a minute in a mixture of heads and tails simultaneously. And this is called a quantum superposition. And it's only when we actually look at this very small quantum coin that it's going to be forced to make up its mind. So maybe it lands in heads. So we could try it again. We can flip this quantum coin of ours. It's going to sit in a superposition of heads and tails initially. And then we look at it and maybe this time it decides tails. Now, of course, when we do this in real life, we're not using coins. We're using things like atoms or their constituent parts or specialized electronic circuits that behave in quantum ways. But whether we're talking about heads or tails or different states of an atom, it seems kind of absurd to think that we can have two separate states simultaneously, heads and tails at the same time. And the reason it seems crazy is if you think of the coin I'm holding here, if I flip this and I don't look at it and I don't look at the outcome, I don't know whether it's heads or tails, but I can tell you for sure that it's one or the other. It's not possibly both. And so how could we know that it's somehow both at the quantum scale before we look at it? So the way we know this is by building a machine like this. Now, what this machine is going to do is it's going to take in one coin on the left-hand side. And if that coin is in heads, it's going to go up and get splashed with some red paint. If instead the coin is in tails, it's going to go down and get splashed with some blue paint, and in either case get sent back out the right side. So what we're going to do is we're going to use this machine on one of our quantum coins. We're going to put it in this superposition of heads and tails simultaneously, and we're going to put it through here. And so of course, when we look at the coin when it comes out, we're going to see just one outcome or the other, heads or tails. But depending on the color that we see, we're going to be able to tell whether it was truly heads or truly tails before we looked at it. So let's give this a shot. We send our coin in, it's going to pass through the machine, and then what comes out is, let's say, heads, but purple. And the only way it could possibly have been purple is if it somehow managed to pick up red paint and blue paint as it went through this machine, just the single one coin. So let's try this again. We put in our quantum coin, it passes through, and this time maybe we see tails as the output, but again, purple. And so the only possible explanation for this is if the coin somehow was able to take both paths simultaneously. That's the only way it could have picked up both colors of paint. And so what this is telling us is that our quantum coin was really truly not in heads or in tails before we looked at it. It was really only us looking that forced it to make up its mind. Now, of course, when we do this in the lab, we don't use coins and paint. We use things like atoms and magnetic fields, but this is very much a real phenomenon that you can see every day in the lab. And we can take it a step further, too, with something that's called quantum entanglement. And the idea here is quite simple. It's just that we can play the same sort of game like we've been doing, but instead of using one coin, we can use several. So let's say a quarter and a penny. And what we could do if we wanted was set it up such that these two quantum coins of ours are going to be simultaneously both in heads and both in tails at the same time. And so just like before, when we look at these, we're going to force them to make up their mind. So for instance, we have a look and they decide to jump into heads. And so we can start this again. We prepared the superposition of both heads and both tails, and we look, and this time maybe we get tails on both. Now, already this is a little odd, because if we just repeated this all day, we would find that we only get both heads or both tails. We never get a mixture of one heads, one tails. Whereas if you took two coins in your pocket, you would get that mixture about half the time. So already this is kind of a funny quirk of quantum physics. But it gets even weirder, because if we start over again and we decide this time that we're only going to look at the quarter, so we're not going to touch the penny at all, we're not going to interfere with it in any way, we see maybe that the quarter this time jumps into heads. And so we haven't looked at the penny, but we sort of know what it has to be, right? Because we started out with both heads and both tails. And so if the quarter is in heads, then sure enough, the penny is also in heads. And the reason this is really bizarre is that we didn't touch the penny, right? So we looked at the quarter, we somehow interfered with it, and this caused it to sort of snap into heads. And yet, as it did this, it's almost as though telepathically it was able to communicate with the penny, as though they shared some sort of invisible link. And when the quarter made up its mind, it told the penny that it should do so as well. And so this sort of invisible link between these two coins is what we call quantum entanglement. We would say that these two coins were entangled with one another. And what's really weird about this is that quantum entanglement doesn't really care about distance. So if you had these two coins right next to each other like they are here, or if you had them on opposite ends of the Earth, this would basically work the same. So these two phenomena of quantum superposition and entanglement are the two main ingredients that we use nowadays to build quantum devices. But before getting into the second part of this, I'd like to bring up one more concept, something called decoherence. Now, this is probably the main challenge in actually building workable quantum devices of the sort that I'm talking about here. And the concept is really quite a simple one. It's that these mixtures of heads and tails simultaneously that we've been talking about, they're very delicate. They're a little bit like trying to balance an egg upright. We can do it, and we do it all the time in the lab, or at least the equivalent. But it has a tendency to just kind of topple over. And in terms of our quantum coin, this means that it'll sometimes just spontaneously collapse to heads or tails, even though we didn't want it to. We didn't do anything to it. And the more coins we have of this sort, the worse the issue gets. So if you think of our entangled coins now, it's sort of like stacking two eggs on top of each other. Again, it's doable, and we do it routinely nowadays, but it's very, very sensitive. So this concludes our whirlwind tour of quantum physics. And now I'd like to switch gears and start talking about how we can actually use these fundamental phenomena that I've been talking about to actually build a new generation of machines, to actually do stuff that is useful for us. Now, the first application I'd like to talk about is something that's called quantum communication. And the basic setup is this. Suppose that you have two people, let's say at opposite ends of town, that would like to communicate with each other. And they're really concerned about privacy. They're concerned about someone eavesdropping on them. And so they'd like to communicate using some sort of secret code, let's say. Now, it turns out that one way in which they can do this, or a piece of the puzzle, is they would start out by exchanging these quantum coins with each other. So these superpositions of heads and tails simultaneously. And they do this back and forth. And it turns out that this will let them communicate in an incredibly secure way. Now, I'm not going to get into all the details of how this works specifically, but let me just give you a flavor for it. Imagine now that there is a third party who's going to try and eavesdrop on this. And so as one of these quantum coins is going by, our eavesdropper is going to have a look at it. And in doing so, they're going to cause it to collapse to one outcome or the other, let's say heads. And then they're going to pretend like they were never there. They're going to step back and pass the coin on to the receiver. But now the receiver just got a coin that was in heads, not heads and tails like they were expecting. And so the take-home message here is that it's extremely difficult to listen in on this sort of thing undetected, right? Because you always leave a trace in the quantum world. And so when we do this in real life, of course, we're not using coins. We tend to use little quantum bits of light for the most part. Now, you already all use light all the time to communicate. For instance, if any of you have fiber optic internet at home, anytime you email someone or Skype with someone, the two of you are communicating by exchanging little bits of light. The only difference here is that we're using quantum bits of light. And so that makes this very, very secure because it makes it extremely difficult to eavesdrop undetected. Now, quantum communication systems, at least early ones, are already available commercially, and they tend to get used in some specialized applications where privacy is at a large premium, so things sometimes involving national security or these sorts of things. And a couple of years ago, even a Chinese team managed to launch a satellite into outer space that works on this exact principle. So what you do is that you beam up these little quantum bits of light to the satellite, it will beam them back down to someone else on Earth, and then this lets these two parties communicate in an extremely secure way with one another. The second application I'd like to mention is quantum sensors. Now, I said earlier that these quantum mixtures of heads and tails simultaneously were very delicate. And you could view this as a bug. You could say that makes it really difficult to actually build devices that use these sorts of phenomena because they tend to be unstable. But you could also view it as a feature, right? You could say something that's very delicate is very sensitive, and something very sensitive could make a good sensor. It's a little bit like if you wanted to go home and make yourself a device that would be able to detect a very, very small earthquake. I would suggest that if you were able to get two eggs stacked on top of each other like this, that would do a pretty good job. That the tiniest little vibration that you would never feel would cause these eggs to topple over. And it's a similar principle when we're talking about quantum sensors. Of course, we're not using coins or eggs, we're using things like individual atoms, let's say trapped inside of diamonds, which is mostly what my research group does. But the principle is quite similar. And instead of detecting earthquakes, we detect things like electromagnetic fields or gravitational fields and so on, but with extremely good accuracy or very good precision. And so there are lots of applications to be excited about here. Some of them include enhancements in biomedical imaging or in material science, or even perhaps in civil engineering, where it could be possible to detect whether or not there's a void underneath the street before digging up the street, because you would be sensitive to the change in gravitational fields where you're standing that would be caused by that. Now, the last application of, or the last emerging application of quantum physics that I'd like to discuss here is perhaps the most famous one these days, which is quantum computing. Now, our current computers are really incredible devices, but there are some problems that they're just fundamentally bad at. And these problems come up all the time in just about every conceivable application, especially in sciences and engineering. And they often have the problem of they often have the flavor of looking for a needle in a haystack, or if you will, trying to find which one of these 10 moving boxes you accidentally packed your car keys into. Now, in this metaphor, really the only way to find your keys for sure is to just go through one box at a time. And so you're going to have to go through all 10. So typically, you're actually not going to make it to the 10th box, right? You're going to find your keys probably somewhere in the middle on average. And so maybe on average, you end up looking at about 5 boxes. But a computational task of this flavor, if you were able to do this using quantum entanglement and quantum superposition as ingredients, it turns out that you could get away with checking 3 times. So 5 versus 3, we're talking about a savings of 2. This is not a huge time saver at this point. It's just kind of more weird than anything. But where this becomes really interesting is when you have a lot of boxes, when you get a big problem. And so if you think of having hundreds of boxes now, there's really no shortcut to this for your average computer, right? The only way to do it is just look through all the boxes until you find the one that you're interested in. But if you somehow could use superposition and entanglement to do this, it turns out that instead of checking hundreds of them, you end up checking 15. Now, I should apologize. PowerPoint decided to sort of mix up how many boxes I have here, and so my number 15 might be off by 1 or 2, but the basic idea is the same, that as the problem gets really big, your computer is going to start to struggle, and your quantum computer is still able to deal with these things quite well. And so this illustrates why it is that we're interested in these things. It's not that we're trying to replace our current computers or make a new generation of smartphone or really anything like that. It's that we're trying to build a very specialized type of processor such that when you encounter a problem like this, you give that only to your quantum processor because it's very well suited for these sorts of things, whereas our normal computers will always struggle with this sort of problem. So a prototype quantum computer, or at least the casing for it, is shown here. This one is by IBM. And the basic mode of operation of these things is that we use a whole bunch of these quantum coins, and we put them all in a superposition such that we somehow kind of try out all the answers at the same time. We kind of check all the boxes at once. And then what you have to do is choreograph this intricate dance of entanglement and superposition such that all these quantum coins kind of come together to spit out the one single answer, so the one box that has your keys in it. Now, this is obviously a very difficult thing to do in practice, and even in theory this is quite difficult to figure out how to do this. And we know that it doesn't work for all types of problems, but there's a lot of really important ones for which it does, and so we're very interested in this. There's been a lot of progress made over the last decade or two, and typically the coins that we use these days, our quantum coins, tend to be things like single atoms or specialized electronic circuits that behave in quantum ways. And really, if we could get a sufficiently large quantum computer built, it would revolutionize quite a number of fields. It would just unlock a whole new area of computing for us. So take chemistry as an application. We heard earlier this morning about the problem of nitrogen fixation. Now, currently, we use about 1% to 2% of all our energy worldwide making fertilizer. And the process that we're using, we know is inefficient because we can see in cells sometimes a process going on, but to actually be able to replicate that on our own industrially often would involve knowing the fine details of molecules like this, and doing so is just beyond the reach of our current computers. But quantum computers would be quite well suited for this sort of thing, and so they have a number of pretty serious real-world applications if we can get them going. Another potential application is in machine learning, where it seems like quantum computers could give us a large boost and potentially take us a step closer towards artificial intelligence. The last application I should mention is that when you buy something online, the encryption that protects your credit card information right now, for the most part, could be broken by a sufficiently large quantum computer. Now, that's not a reason to go out and build a quantum computer, and also you would need a really big one to do this, like way, way beyond what we can foresee in the coming years. So you really shouldn't worry about this in the near term. I just felt as though I would be shortchanging you if I didn't at least mention this, because this is a favorite of reporters when you see newspaper articles on this sort of thing. So this all brings us to the end of the story, and in particular to the million-dollar question, or in this day and age, the multi-billion-dollar question, which is, when do we expect these things to mature? So as I said earlier, the main difficulty in building these sorts of devices is dealing with decoherence, is dealing with the inherent instability of quantum systems. And I've introduced these three things roughly in level of increasing difficulty. So as I said, quantum communication is something we already do now in some limited capacities, and you can expect to see more of it in the future. Quantum sensors are still a few years away, but they're on their way. Quantum computers are, I would say, the highest risk and highest reward on this list. They're anywhere from several years to several decades away for big ones. It's really anyone's guess at this point. And that is, of course, assuming that we get there at all. But the way I see this playing out is in the near term that we're going to start seeing quantum technology behind the scenes. So you might go to the pharmacy someday and pick up a prescription for a new drug that was developed with the help of a quantum sensor, although I wouldn't necessarily say that on the label. In the longer term, though, I think there's an analogy to be made between quantum physics and solid-state physics. So namely, solid-state physics is what gave us the integrated circuit and the microprocessor in the last century, which is what led us to our current era of laptops and smartphones and everything we know and love today. And I think there's a similar case to be made for quantum physics, that it too could usher in its own technological era. Now, I've only been able to scratch the surface in this talk here, but I encourage you to read up on this because it's really a promising field, and to ask me any questions you might have and to come chat afterwards. And so on that note, if there's any time remaining, I'd be happy to take questions. Sure.
So you mentioned that machine learning could be a possible use for this. And I know one of the big kind of themes these days in machine learning is explainability. And so how in quantum physics, given that it's already very difficult to kind of even explain what's happening,
Yeah.
is there talk about that as it develops, like to make sure that that's a piece as they develop the science, that explainability is incorporated into that?
That's a great question. Oh yeah, absolutely. So the question was, in machine learning, as is one of the quirks of this field, is that it can make often fantastically accurate predictions about things, but it doesn't tend to tell you how it came to that decision. And so this is really a problem. Like if you're trying to decide on a medical treatment or something, you'd like to know why it gave you this particular course of treatment. And I'm actually not aware of much work in this direction in the quantum fields. Typically, people tend to focus on sort of the raw computational power of how could we use more data and have higher accuracy and so on, but that's a really good point.
Okay, we'll move on to our last talk.